In this video, I'm going to do a paper summary of the Hypencoder Hypernetworks for Information Retrieval paper by Killingback, Zhang, Zamani from UMass. I'll start with main takeaways, then I'll talk about their motivation for doing this work, then we'll go into the Hypencoder overview, query and document encoders, talk about the hyperhead layers that produce the weights and biases for the QNet network. Then we'll talk about how they do efficient retrieval using Hypencoder, compare the Hypencoder architecture or framework to the existing neural IR methods, look at some training details, and then look at their results. I had 5 main takeaways from this paper. First was related to their motivation, which is that when using inner product relevance scores, there's always a set of relevant documents which cannot be perfectly retrieved. Hypernetworks are neural nets which produce the weights for other neural nets. Hypencoder is a hypernetwork. Each query embeddings is fed into the Hypencoder to create its own neural network, which takes as input single vector document embeddings and outputs a relevance score. Hypencoder-based retrieval uses a graph-based greedy search algorithm, and Hypencoder outperforms strong, dense retrieval models and larger re-ranking models. So this is the first time I've read a paper related to hypernetworks, and I just find the concept so cool. So that was a really interesting aspect, among other things. Overall, it was just a really interesting paper for me to read. So we'll start with their motivation, where they talk about something called Radon's theorem. And according to Radon's theorem, any set of h+1 document vectors with h dimensions can be partitioned into 2 sets whose convex hulls intersect. For any h+2 vectors, the 2 subsets of a Radon partition cannot be linearly separated. In other words, for n, where n is the number of documents, greater than h+1, there exists at least one group of documents that is not linearly separable from the rest. In the real world, since n is much greater than h+1, there are indeed many such non-separable subsets. So for example, n could be 13 million documents, and h could be 768 as the dimension that you're embedding your documents and queries into. So obviously 13 million is much greater than 768 plus 1. So a couple things. I'm going to look at what convex hulls means, and then we'll look at an example of illustrating this concept. So in geometry, the convex hull may be visualized as the shape enclosed by a rubber band stretched around the subset. And this was from Wikipedia. So let's look at an H of 2, so 2D space, and let's look at H plus 2 vectors. So 2 plus 2 is 4. So we have 4 vectors. Let's say they're 4 documents. So we have embedded these documents into 2-dimensional space. Documents AC are relevant and documents BD are irrelevant, and the convex hulls intersect. So AC, if we had a rubber band around AC, it would be this turquoise line, this vertical line, and then the rubber band around BD would be this horizontal line. So this is kind of conceptualizing that piece of Radon's theorem. And then we can see that if we wanted to separate our relevant documents AC from our irrelevant documents BD, we would need some kind of nonlinear function, right? So there's no straight line that could separate AC from BD. So if we had a horizontal line here, we could separate A from BDC. In that way, we could separate B from ADC. So we could separate one of these from the other 3, or we could separate any 2 that are next to each other. So A and B we could separate from DC with a straight line in the middle, so AB DC, BC AD. So we could, draw these lines and separate some of them. But here is a configuration AC and from BD that we can't separate with a linear line. And so we need a nonlinearity. And anytime we need a nonlinearity, we throw a neural net at it, right? So we want some kind of squiggly function, and neural nets are great at approximating that for almost anything. So in the real world, Since our number of documents is greater than h plus 1, there are indeed many such non-separable subsets. So even with h plus 2 vectors, we have this situation. Obviously, we imagine millions of documents. You're going to have all sorts of pockets of relevant documents that you can't linearly separate from irrelevant documents. So what is this emphasis on linear about? Well, inner product is operation that linearly separates two subsets. So if I had a query Q, I had a document D1 and a document D2, and these are all embeddings. So let's say these are embeddings in two-dimensional space. Let's say I take some type of inner product operation where I'm projecting D1 onto Q and I'm projecting D2 onto Q. So we have this projection dashed lines, which are projecting D1 and D2 onto Q. So, let's just say, cosine similarity, for example. And let's say these are all unit vectors. So I say, okay, anything above 0.5 magnitude in terms of projection I'm going to consider relevant. And anything less than 0.5, I'm going to consider irrelevant. So this relevant and irrelevant documents are separated with a line. Right? This line is perpendicular to Q at half of its magnitude. So this is an example of how inner product type of operations create linearly separated relevance for our documents. And as we saw in our previous example, there's going to be eventually, once we get to a large enough number of documents, two more than our dimensionality of the embeddings, we're going to get to a place where we can't linearly separate it. So this is why inner product does not work for our retrieval purposes. There's always going to be a subset of relevant documents that we can't separate with just a straight line. So just, that was my understanding of it. This is the first time I've heard of Radon's theorem, and it took some effort to understand it. So if that's not the best way to explain it, please let me know in the comments below. But I thought that this was like a really good way in the paper that they presented to set up the motivation for the Hypencoder. So the Hypencoder is constructed of a hyperhead, where the hyperhead takes your query encodings or embeddings that are passed through BERT, and it produces a set of matrices and vectors that are then used as the weights and biases for a small neural network, which we coin the QNet. So the query gets encoded into vector space. That vector gets passed through the hyperhead. That hyperhead outputs weights and biases that we then put non-linearities in between to create a neural network, and that neural network is called QNet. And to find the relevance of a document, the document representation, ED, is passed as input to the QNet, which outputs the relevant score. So our document also gets encoded, and we get our ED embeddings. That becomes the input for our QNet, and it spits out a single float value, which is our relevance score. So the main takeaway from this diagram is that the Hypencoder framework is representing our query as a neural network. And that neural network is related to the encoding of the query, because the hyperhead is trained to take some encoding, and based on the encoding, it generates weights and biases. So if you change the encoding that goes into it, it's going to provide different weights and biases, and that's going to make a different neural network for different queries. So really interesting idea. And these neural networks are, less than 8 layers. So these are very small, relatively speaking. I mean, incredibly small neural networks. So, they don't increase the latency. So it's a very efficient way to do this. We're going to take a real quick look at some of the code. So this is from the Hypencoder repository on GitHub, and this is their quick start code. So they have this Hypencoder dual encoder, and the dual part is that we have a query encoder and we have a passage encoder. We load the tokenizer as usual from auto tokenizer. Then we take our query strings and passage strings and we tokenize them to get our query inputs and passage inputs. Then we take our query inputs and we pass the tokens to the query encoder, and it returns back our QNets. So it returns back neural nets. And the passage encoder will return back passage embeddings. Then we take those passage embeddings, we pass it through the QNets, and we get back our relevance score. So obviously a lot of detail that I'm just kind of glossing over, but I wanted to show this as a kind of visual to support the diagram that they have in the paper. All right, so let's talk about the query and document encoders that we're dealing with. So these encoders are BERT-based model for encoding queries and documents. They use a single vector representation of documents, and in particular, they use the contextualized embedding that represents the CLS token, which is 768 dimensions. And for queries, they don't use a single vector, but they use all non-pad token query token representations. So if a query has n equals 32 and h is 768, that 32 by 768 vector is used as input to the Hypencoder, and then that produces the weights and biases from which we construct the neural network QNet for that query. A quick aside on the CLS token, some screenshots from the original BERT paper. CLS is a special symbol added in front of every input example. The first token of every sequence is always a special classification token, CLS. The final hidden state corresponding to this token is used as the aggregate. And this final hidden vector corresponding to the first input token is the aggregate representation. So CLS kind of represents the aggregate of the entire sequence. And in the paper, they talk about using the average document token as the representation, and they found that using the CLS tokens embeddings gives them better results. And in terms of input, we just literally have a CLS token at the start. So that's what we're talking about visually speaking. All right, cool. So we have these hyperhead layers, and they produce the weights and biases that are used to construct the QNet. So let's walk through how exactly we go from query token embeddings to weights and biases, and we're going to focus on the weight matrix because in the paper that's what they show, and they say that the bias vector is constructed similarly. So the contextualized query embeddings, EQ, produced by the query encoder are independently transformed by L hyperhead layers, each of which corresponds to a layer in the QNet. And again, by default, they use 6 layers in the QNet. So each hyperhead layer converts the embeddings EQ first into key and value matrices. So EQ is our query token embeddings. This semicolon 1 means that it's concatenated with a column of all ones, so that matrix multiplication will include both weight multiplication and bias addition all in one operation. And then theta ki and theta vi are weight matrices that are h by h, and these are learnable parameters. So that's part of what gets trained when you're training the Hypencoder. And so you multiply these learned weight matrices by your query token embeddings to get your K matrix for that layer. So Ki, where I is the ith layer, and you get your V matrix for that layer. So this is the first kind of intermediate output of the Hypencoder. So query token embeddings go in, and we multiply by our learned matrices, and we get a K and V matrix. Then we also have a query QI, so kind of confusing because this is also query, and then the query itself is also the query, but this QI query where we're talking about, attention mechanism query, that is also a learned set of embeddings, and that is also for each layer of the QNet. And so we take our capital Q learned matrix, multiply it by K transpose, divide by the square root of H, and we multiply that by the V value matrix that we got from the last step, and we take the softmax of QK over square root of H. So this is our scaled dot product attention. And the output of that is called HI. So again, I is a given layer of the QNet. And for all layers except the last one, HI is a square matrix. So everything here so far is a square matrix. The last layer, it outputs a single float value, so it's going to be not a square matrix. Okay, so now we have this attention HI matrix. We pass that through a ReLU, and then we pass that through a layer norm, and then we multiply it by another set of learned parameters, phi wi and phi bi, and each weight in QNet, and I think I interpreted this as each layer in QNet has a unique theta w and theta b. So theta w gets multiplied by the output of our ReLU of L norm applied to our HI attention matrix, and then we add on our bias vector. So we get this H hat I matrix, and then the final step, which gets us our weight matrix that we're going to use in the QNet, is going to be to take that H hat I and we're going to add to it a learned matrix theta HI. It's the same size as H hat I, and it acts as a base weight, which allows the model to learn universal query-independent patterns that are applicable for all queries. So I thought that was a really interesting concept. It's kind of like, you know, the like a y-intercept, or like an average query representation for this weight matrix. And that would be, you know, interesting to think about, like how, you know, queries themselves universally kind of share some meaning that this represents, regardless of the nuances and details of the specific query. And so that creates Wi, and then that Wi is the weight matrix that is used in that layer for the QNet. And in the same way that we did this, they also create a bias I for that particular layer in the QNet. So putting everything on one screen, we start with our BERT encodings of our query tokens. We get our K and V matrices for that layer. We calculate scale dot product attention, and we get HI matrix. We pass that through a ReLU and an L norm, multiply that by learned weights, and add a learned bias, and we get our H hat I, and then we add some universal representation of query tokens, theta HI, which is learned as well during the Hypencoder's training, and we get our final weight matrix for that QNet's layer. And during their experimentation, they tried 2 mechanisms to do this transformation, as well as many minor variants, and found them all to have stable training, which suggests the Hypencoder framework is robust to the exact hyperhead layer implementation. Okay, so we have our weights and biases that are based on the query token embeddings. Now we can construct our QNet network. So weights and biases produced by the hyperhead layers are not by themselves a neural network. They need a certain arrangement and additional components, for example, a non-linearity. And this is where the Hypencoder's QNet converter comes in. The converter knows the architecture of the QNet, and given the weights and biases from the hyperhead layers, it produces a callable neural network object, which takes as input the document representation E sub d, and then it outputs a single float relevance score. So in their experiments, they use a simple feed-forward architecture for the QNet. The output xi plus 1 based on the document for the input xi of the document at a given layer I is given by this equation. So in the very first layer, xid is ed, it's the document embeddings. That gets multiplied by the weight that the hyperhead layers created given query tokens. And we add the biases, or the bias vector, that was also created by the hyperhead layers. We pass that through a nonlinearity, and then we pass that through a layer norm. We do a residual addition of our original, and that becomes the output of the layer, which then goes into the next layer. And this layer in equation 6 is repeated L times. Finally, a relevance score is produced using a linear projection layer with an output dimensionality of 1. Okay, so that is the kind of architectural overview of the Hypencoder and the hyperhead layers that take the embeddings of the query tokens and generate weights and biases that are then constructed into a neural network, and that neural network takes in our embeddings of the document, single vector representation, and outputs a relevance. Now we're going to look at the efficient retrieval using Hypencoder, which is algorithm 1. And we start by creating an index, and in the index stage, they construct a graph where documents are nodes, connected to their neighbors by edges, and they use L2 distance between document embeddings. So they didn't say what the threshold was for an L2 distance for two documents to be considered neighbors, but I imagine that there would be some kind of threshold L2 distance above which we would consider two documents to be neighbors, and therefore they would be connected in this graph with an edge. So on the left-hand side, we have our algorithm, and on the right-hand side, we have annotations. So let's look at the input itself. The inputs to this algorithm, we have our QNet, Q, so that's a neural network. We have the number of nearest neighbors that we want, that's K. We have our initial candidates, C tilde, which is a set of initial candidate documents selected at random. Then we have number of candidates to explore at every iteration and candidates, so that's an integer. And then we have max iter, so how many times we want to run this search loop. That's also an integer. And the output is going to be the K closest neighbors to Q. And our K closest neighbors, so remember these are documents, document embeddings, they're going to be stored in capital T. So capital T is our set that stores the top K nearest neighbors. So I'm going to focus from line 4 onwards. So we have this initial candidate set of documents, tilde C. We pass those documents through our QNet, and we get a relevant score. And then we sort them, so we have the highest relevant to least relevant. Then we pick the top n candidates, so the top 100 or 128 or 64 or whatever n candidates is. We pick those top n candidates based on highest score, and we save that in lowercase c. And then for f, it's a variable that stores the lowest scoring element from t, which starts out as set with negative infinity. And then this first line here, or this first break opportunity, line 7 and 8, if the maximum score in our lowercase c set of documents is less than f, then we're going to break this loop. So if the maximum score in C is less than the lowest score in T, we're going to early stop the search. So this is what they call early stopping. If not, we keep going. We're going to reset C to an empty set, and then, C tilde to an empty set, and then our lowercase c, which has our top n candidates based on score, relevant score, we're going to look at each element, and we're going to go through this condition. So for each element in C, get the lowest scoring element from T, pass the document E through our QNet, and get a score. And if that score is greater than F, or the size of T is less than the number of nearest neighbors we want to find, then add that document to T. So real quick, we're just, I think it's interesting to note that this whole decision on whether we want to add this document to our final set of K closest neighbors to Q is based on whatever the lowest scoring element from our last iteration is. And if adding that document makes T get larger than K, then we remove whatever that lowest scoring element was. So yeah, I think this is also an interesting concept. Initially I thought, I'm like, oh, this is kind of like first in, first out, but I don't think that's quite the analogy that we should use here. But it is interesting that over time, if the documents that we're searching exceeds the number that we want to retrieve, K, then we're going to start dropping off the lowest scoring document. So I think over time, the average score of our set T is going to increase. So cool. So we've updated our set T. And then we're going to look at all of the neighbors of our document E. And remember that the document graph is already created, so we can look up what the neighbors are. And then for each neighbor, if it's not visited, then we're going to add it to our empty set, C tilde. So we're going to visit it in the next iteration. And then we're going to say that we have visited this document. So V is the set of visited elements. So in this way, we kind of keep going quote unquote farther and farther down our graph, and we visit more and more documents. What I think is really interesting, and this is, we'll kind of see the consequence of this in the results, is that here in line 1, our initial candidate set, which were our randomly selected documents, that gets stored as our set of visited elements. So we only add a neighbor to our empty set of ~c. It's not in our set of visited elements, but from the get-go, our initial candidate documents all are considered as a set of visited elements. That's kind of point 1. Point 2 is that in the first line, in our iteration loop, we only select the top n candidates in C tilde. So let's say C tilde is 10,000, right? So we have initial candidates set of 10,000, and let's say n candidates is 128. So we're only storing 128 candidates, and the other, what is that? 9,900, 62, 72? All of those are considered, or 9,872, all of those are considered visited. So 9,000 plus documents from our initial set do not get revisited in our algorithm. And there are some consequences for that, which we'll see later on. One other point, which I think we'll also see in some of their ablations, is that if the maximum score in C is less than the lowest score in T, we should early stop the search. And the logic here, I understood to be, is that if these quote-unquote closer documents are not relevant, then these farther neighbors won't be relevant either. And that's not always the case. Okay, so that's the algorithm they use, and it's a very efficient retrieval, and they test that out, which we're going to look at in the results section later on. One more thing before we go into training and results is we want to compare their approach to existing neural information retrieval methods. And these existing methods have a document representation, ED. They have a query representation, EQ. They have some combination function, FC, which combines the document and the query. And they have a final neural network that takes the combined document and query representations from FC and produces a score, and that neural network is, we're going to call it FS. It's some function. And what they're saying is that all 4 of these elements are represented in the QNet, because the QNet takes as input the document representation, so it covers that. The QNet itself is made from the hyperhead layers given a query representation, so it covers that. The combination function, the QNet, is already combining the two in that sense in terms of representation, so we can check that off. And the final neural network, well, the QNet is a neural network, and it does produce a score. So f of s is also covered by our QNet. And so that's how I understood this section, that the QNet itself is capturing, and really the Hypencoder framework in general is capturing all 4 of these points. There is one difference, which is the weights of FS are query dependent in our case. However, this can be remedied in 2 ways if we want to make this similar to existing neural IR methods. We can have shared weights, or the weights for FC can have a common non-query dependent base weight, similar to our implementation. And so if there's no benefit using query dependent weights, the shared weight can be used. But if there is additional benefit, the model and optimizer can learn to take advantage of it. So this goes back to this idea that that we had that theta hi that gets added on to that h hat sub I, and that theta hi is like some average or some universal query independent weight that represents some kind of basic information about what queries contain in general. Cool. So now we're going to go into training details. So their training data set was the training split of MS Marco, which was 8.8 million passages and about 500,000 queries. They constructed training pairs by first retrieving 800 passages per query using the early Hypencoder iteration. Then they sampled 200 passages from those 800, where 100 of those were the top 100 scoring, and then they randomly sampled another 100. And then they labeled query passage pairs using mini-LM cross-encoder, which is a strong model for scoring query passage pairs. So I understood that to be like the distillation aspect of this. And then they used a subset of Trek Deep Learning 21 and 22 for the validation dataset. And then they had in-domain, out-of-domain, and hard retrieval evaluation datasets. Some training details. BERT-based uncased was the base model. The QNet has a hidden dimension of 768, and it takes an input of 768 dimensions from BERT. And it has 6 layers by default. Passages are truncated to 196 tokens, and queries to 32 tokens. And each batch item is one query, one positive, which is a top ranked by teacher model document, and then 7 randomly selected documents. And the loss function for training is the margin MSE loss, which is averaged for the 7 triplets of query, positive document, negative document. So the positive document stays the same in each triplet, and the negative document goes through each of the 7 random documents that they selected. They use in-batch negatives, and they use cross-entropy loss for that, where the positive document for the other queries in the batch are considered the negative document for the given query. So that's why it's called in-batch negatives, because the negatives come from the other triplets in the batch. And training took 6 days on 2 A100 GPUs. All right, so let's look at some results. I'm going to highlight some interesting things that stood out to me. I mean, the main takeaway is Hypencoder is outperforming single vector dense retrieval methods and BM25 most of the time, and it's competitive with other retrieval methods. So that's kind of the main takeaway. I want to highlight here that Hypencoder exceeds the performance of Dragon, MonoBERT, and CrossSim LM. MonoBERT and CrossSim LM, I understand, are re-rankers. And Dragon is, it uses the same base model and is a bi-encoder, and it uses 32 A100s to train, 40 times the training queries, and a complex 5-teacher curriculum learning distillation training technique. In other words, Dragon is likely close to, if not the ceiling for BERT-based bi-encoders, and still Hypencoder is able to match it with a simple distillation training setup and far less training compute. So again, really impressive what they've been able to do with this Hypernetwork QNet representation framework. Highlighting their out-of-domain results, I'm highlighting that it's interesting that 2 out of the 5 evaluation sets had BM25 as the best performing. So it just goes to show that BM25 is a very strong baseline. And a point of note is that even for harder retrieval tasks, their Hypencoder performs better than all of the other baselines for almost all metrics for all of the retrieval data sets. Here was that reference to latency. So their algorithm is efficient 1 and efficient 2 in this table, and it has a fraction of the latency when compared to exhaustive search with comparable performance for retrieval. The number of QNet layers should ideally be around 4 to 6, and it's interesting that at 8 layers the performance drops, and they said that this could be because they didn't train it long enough. So if you wanted more layers in your QNet, you would have to train your Hypencoder longer. And then here's where we get into some of the really interesting points that refer back to our algorithm 1. So they ran some ablations where they're changing the initial candidate set tilde-c from 10 documents to 1,000 documents to 100,000 documents. And the solid lines are with the early stop, and the dashed lines are without the early stop. And the blue line here, these blue lines are the retrieval metrics on the left, and then we have query latency on the right. So I want to focus on 2 things. Number one is that without the early stop, you do capture some additional retrieval performance. So the assumption that if the next set of candidates maximum score is not greater than the lowest score so far, then we don't need to keep searching. That early stop is not always beneficial. So that assumption that we need to stop searching just because our next set of candidates maximum score is not higher than our lowest score, that assumption is not always true. So I think this also kind of ties back to the radon theorem's, kind of main point, which is that we can have these like unexpected groups of relevant and irrelevant documents. And so even farther down the document graph, even though we're getting farther and farther away from what we would consider similar documents, we may encounter like a pocket of documents that are still relevant. And so that's how I interpret this increase from with early stop to without early stop, given the same set of initial documents. And then another interesting feature of this ablation is that after some point, increasing the initial document candidate set actually worsens the performance. And the explanation they gave is that, if you recall here, we consider all of our initial candidates visited right from the get-go. And so later on, when we're adding neighbors to our empty set of tilde C, we only add them if they're not in the visited set of if they're not in the set of visited elements. So you could have a very high initial candidate set, but we're considering them all of them visited, even though we're only scoring inside of our loop, we're only scoring the top n candidates and then kind of dealing with those. So if you have a very high initial candidate set list, you could have maybe 10,000, like I said in my earlier example, but you only have 100 n candidates that you're considering, or 128. We have almost 10,000 candidates that we're basically throwing away and we're not revisiting. So that was their explanation here, that once you get to a very large number of initial candidates, you actually end up throwing away potentially relevant documents, and so our retrieval performance decreases. Yeah, so that was their ablation with the size of initial candidates. Then we have n candidates, which is the amount that we're selecting top scores from inside of our loop. And I think the most interesting thing about this chart is that there's a very sharp spike in the beginning, and then it kind of flattens out. So, after maybe 50 or so candidates, you don't really get that much improvement, maybe a percentage or two. And we kind of see the similar thing with max iterations. So after 12 iterations, we don't get any increase in performance. And I think, the concept there is, I hesitate to say this, but, because we already saw that early stopping doesn't always help. So, I think there's this like trade-off that like the farther you go down the document graph, you might encounter some documents that are relevant. But if you go, after 12 iterations, you're on your 12th set of neighbors that you're visiting, at that point, you've kind of exhausted the number of relevant documents that you're going to encounter. So I hesitate to say that because early stopping doesn't always work. So, there's not necessarily that max iteration, which kind of has the same concept, is tapering off or plateauing off because of that logic. But yeah, that was kind of an interesting, tension between neighbors being relevant and, finding those pockets of documents deeper in your graph, even though they're farther away in terms of L2 distance. Cool. So that's it for this paper. Really, really interesting concept. I mean, hypernetworks just seem so cool. They sound so cool and they seem so cool. This concept of taking query token embeddings and generating weights and biases to create a neural network. I mean, what a cool concept. And obviously it's really powerful. So definitely this has put me onto Hypernetworks. I definitely want to keep exploring that. And something I wanted to reference from a couple of months ago, Omar Khattab, who's the Colbert OG, he tweeted out, and I'll just read this. When building Colbert, I assumed it will pave the way for hypernetwork-based pruning-capable retrieval indexes. The big insight in Colbert is that we can encode each document upfront, not into a vector, but into a rich scoring function, f, where you take a query and you get a float, which simultaneously supports pruning, so you can skip most computation. In V1, V2, the choice of function was a matrix with max similarity. It showed that at inference time, we could do a lot better than dot products. But in the future, the function could also be a small, dense neural network constructed out of each document. The encoder is then a hypernetwork producing functions f with the same query float signature, allowing each document to decide its strategy for deciding if a query is relevant to it. How to do this while allowing pruning so that retrieval is sublinear at scale is a rich question you can steal if you're doing NLP systems or information retrieval. So, free game that he's putting out, just really, really interesting concept, really powerful concept, especially, seeing that 4 to 6 layers was enough for a QNet to allow this hypernetwork concept to be performant. Maybe even smaller networks can be used for documents because there's so many more documents than there are queries. Who knows? But I just wanted to drop this here as a point of inspiration. So that's it for this video. Thank you for watching. I'll be doing some more information retrieval content, hopefully in the next week or so. So looking forward to having you all watch future videos. Thank you.